The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to our eSeminar today entitled Next Generation Calibration App in the 3DEXPERIENCE platform. My name is Vanessa Clemens and I'm the host of the meeting. I would like to introduce our presenter, Todd Dalrymple. Todd has held many positions within the SIMULIA organization. He has worked as the Engineering Services Manager and later the General Manager of the Great Lakes CSE in the USA, and is now working for the SIMULIA R&D organization, focusing attention on how we deliver advanced material modeling technology to our customers. The presentation today is about 45 minutes. There's a full screen button in the lower left corner. You can type in questions during the event and we will answer those as time permits at the end. To type in a question, please use the Q&A dialog. A recording of this eSeminar will be made available. You will be informed by email as soon as possible. I'll now hand over to Todd, who will start the presentation.
Well, thank you so much, and welcome everyone to our eSeminar on our new calibration app. As Vanessa introduced, I've worked in a number of positions within the company, and I've always been interested in material modeling across many different industries as well as material types. And very happy to say that we're continuing both to develop new material models for advanced modeling and also a calibration app in order to ease your ability to use those advanced material models. So the very first slide of my presentation, I'd like to take a shout out to the learning community, the SIMULIA Learning Community. If you've not been to the learning community, I would really recommend that you go there. There's quite a lot of material for the subject of material modeling and calibration. And this is really all you have to type into your browser is 3ds.com/SLC. And I'm going to move a browser into my screen for the moment. And I'm going to just type in 3ds.com/SLC. And I'm going to hit enter. And how you could navigate, so I'm now in the SIMULIA Learning Community, and I would use this little wiki area in the upper right-hand corner and scroll down, and I would see the material modeling and calibration, an overview, and curriculum. And if you clicked there and then clicked on this hyperlink, the title post, you probably want to bookmark this page right here. So this is organized as a post of posts. This post right here serves as the master post, almost like a table of contents. And there's I've been building the subject matter here over the last few years. There's a lot of calibration-centric ideas and a lot of just general information about material models. For our new calibration app, you could click on this hyperlink right at the very top, and this post shows some slides as well as some narrated videos demonstrating the app, but demonstrating it in the 2018X version. So this was a version that was out in the late summer of last year. And you'll notice this PowerPoint slides have a date of May 2018. So if you're welcome to watch those. That the UI has changed a little bit since 2018X version, but then down near the bottom, but much has remained the same. Down near the bottom, you could click on this hyperlink and notice that it says an update on the calibration app for 2019X, FixPack 1923, June of 2019. So the app has been released just about a week ago for on-premise, and we'll get into this in some of the slides. So I'll just click here, and again, now this post is all about the 2019X version that has just been released. So you probably don't necessarily have access to it right now, given that it was just released. And in just a few more weeks, the on-cloud version, the public on-cloud version, will be updated to this FixPack. So we have, again, a few slides and then quite a few narrated demos of how to use the tool for a broad variety of material models. So again, I just wanted to to give that little shout out to the learning community and a lot of material model resources that are available to you there. So we'll get into the slides proper. I only have 10 or 12 slides here, and I want to use the bulk of the time to do a live demo. And I'll apologize in advance if anything goes wrong. Anytime you're doing a live demo of software, all sorts of little gremlins can creep in. But the outline of what we're going to do today is just talk about calibration, a little bit about the motivation and background, the calibration status. I said before, we released this tool in 2018X version of the 3DEXPERIENCE platform with what is called HotFix 4, again, last year. We'll talk a little bit about our development roadmap, what we've worked on already and what we're planning on working on in the near future, over the next year, year. And then we'll do a live demo of the app. So I'll tend to go through these slides relatively quickly. Again, I'm quite available to interact with customers around material modeling and calibration issues. But why calibration? Well, you know, Abaqus offers a lot of advanced material models, but over many years in which I've interacted with customers, what I find is that some of our highest end customers who really need to use some advanced material models put in a lot of time, energy, and money into understanding how to calibrate these material models, how to test for these material models, how to turn test data into material model parameters. And calibration really is an enabling technology. It enables you to get over that hurdle and to start using some advanced material models in Abaqus. And I've seen many instances where I wished it would have been possible for customers to more quickly, more readily use some of the advanced capabilities. There has been some hyperelasticity and Prony series viscoelasticity calibration tools available in Abaqus CAE for some time, and we really set our goals for the first release of this 3DEXPERIENCE app to meet or exceed those capabilities, and I really think we did that, and I'll comment on that throughout, especially the demo. Well, what is calibration? In a simple way, the calibration is one wants to create a mathematical model of some observed behavior. So typically in the material modeling area, the observed behavior is say a monotonic pull test, a cyclic test, stress relaxation test, a creep test, all sorts of different kinds of tests that one could run to see the behavior of a material. Does it have permanent set? Does it have time dependent or just time independent behavior? Once we have observed the behavior through testing, then we want to construct a math model, and we construct that math model through a process of calibration. And in our first bit of work on this app, which is encompassed with both the 2018X and this very recent FixPack release of 2019X, we've really focused on constitutive models. And we'll say more about that in the next few slides. But there's a lot we could do beyond simple constitutive models, that is stress strain models. We could start to calibrate damage, say ductile damage of metals, failure of composites. We could calibrate fastener constructs, connector models, and I'll show a few slides of what we're working on and what we're hoping to work on over the next year or two. So if you had gone into the 2018X version, HotFix 4 and HotFix 5, you'd see this group of materials supported. And this group of material support was all done in what we call the analytical kernel. So all the equations for these material models were written from scratch in a very fast analytical kernel. So in 2018X of the software, the behavior, the calibration was very fast, and it had nothing to do with Abaqus. There was no running Abaqus in the background. So that was very nice. We focused a lot on performance. And another thing that sets this apart from the Abaqus CAE functionality is that the Prony series viscoelasticity elastic calibration with hyperelasticity is performed in a fully integrated and simultaneous fashion. And what I mean by that is you give some test data, and we'll do a calibration of a family of rate data to make this point. But if you went in and chose the hyperelastic plus prony viscoelasticity, or the one with Mullins, those calibrations would simultaneously determine the best set of parameters for both the hyperelastic part and the viscoelastic part. And that is significantly different than what was done in Abaqus CAE. So this slide gives you a bit of a summary. Everything in red, I'll let you read through this slide, but everything in red are things that we delivered in the HotFix 5 version of 2018X. We did a lot of work on infrastructure, UI design, providing a UI, this analytical kernel or analytical mode that I mentioned. And of course, we worked a lot on optimization algorithms. We thought, thoughts about error measures, error norms, many things that you would be familiar with having used previous tools like the tools in Abaqus CAE, or perhaps using a general purpose optimizer like iSight. So we certainly have a lot of experiences with optimization and calibration in our backgrounds, and we really tried to make a tool based on many years of feedback from our customers. The stuff in blue in the lower left area were things that we had on our list, and we just really didn't have time for it in the 2018 X release, and became the target for what we would release in 2019 X, and in fact did just release. A little bit more of a sort of a graphical map, or a color map, if you will. This level 1 development was delivered in 2018 X. It's using an analytical material response evaluator, that is the analytical kernel or analytical mode, very fast performance, and supports hyperfoam, hyperelasticity, and hyperelasticity with viscoelastic and Mullins effect. And then we went on to work on level 2. So level 2 is the things we've been working on for about the last year, maybe 8 months. And level 2, what we realized is that if we continued along and kept writing material model equations from scratch, it could take us many years to get a broad scope of material model coverage in our calibration tool. So we felt that a faster way of adding a lot of material model coverage was to develop a lightweight way of calling Abaqus standard and dropping down into just the material routines of Abaqus standard, passing in a strain time history, and getting back the stress. So we have this new lightweight Abaqus material response procedure. It was just released a week ago, and it opens up access to many Abaqus material, to be very specific, Abaqus standard material behaviors, including UMATs. And so that's quite an interesting thing, that you could use our tool to calibrate your own UMAT. Level 3 is things that we have on our roadmap for future development, ongoing future development over the next year or two. We really like to get beyond simple constitutive calibration and deal with things like damage and failure. Abaqus has and has had quite a large array of capability for modeling damage and failure for a number of years now. And again, as I interact with customers, my takeaway is that most customers, if they have a really strong need for this, they'll spend a lot of their own energy and time and money figuring out how to calibrate those damage and failure models. But if they don't, they sort of just skip over it and say that's just too difficult and too time consuming. So we would like to address damage and failure, both of things like ductile damage of metals as well as damage of composites. So this release that we just released last week, again, a summary here, we have this new lightweight Abaqus standard material response procedure. It, as I said, it opens up an access to many Abaqus standard material behaviors. The on-cloud version is planned to be released in the first week in July, or the end of that first week. That might be a little bit interrupted by the July 4th holidays here in the States. One thing I'm not going to show in the demo, but we do have in this release, a very first release of stability checks, and I'll take a moment to comment on that. Abaqus CAE has always had in its hyperelastic calibration the ability to tell you something about whether the material parameters that have been determined lead to a Drucker stable or Drucker unstable material model. And over the years, many customers have said to us, well, that's nice that you're telling me whether it's unstable or not, but it'd be nice if I could simply ask the tool to produce a guaranteed stable material. And so with lots of feedback on that, we have been working on a tool both in our app to show you the stability, but also to affect the stability or guarantee the stability. And so this is a very first release of that feature. And I think we're going to continue to gather feedback on that and continue to work on that area of the tool. I think there's a lot of power there, and I think something that could really change how one thinks about material modeling if you really could get a guaranteed stable material model. We've also been working on test data pre-processing. We know that as you bring in test data, sometimes cleaning up the test data, decimating the test data, doing things like zero shifting and smoothing enhance the calibration process tremendously. Sometimes it can really make a big difference between achieving a good calibration or not achieving it at all. So if you were to open up the 1923 fix pack of 2019X version of 3DEXPERIENCE platform and go to the calibration tool, you would see this image on the left is all of the material models that we cover. They're sort of all rolled up. And we list just sort of the base state of that material model. And if you unfolded them all, then you would see this image on the right. So we now can do many different kinds of linear elasticity, add plasticity, add creep, add both plasticity and creep, add Prony series to simple linear elasticity, do all of these things with hyperelasticity, with hyperfoam, and I'll let you read down through that list. We also targeted the parallel rheological framework model. We had a lot of customer requests for that, and because it's so similar, we also addressed the two-layer viscoelastic model. There is some overlap, so this becomes what we're calling this is the numerical kernel or the numerical mode. And there is some overlap between the analytical mode, but in the analytical mode, you can do hyperelasticity. You can do hyperelasticity plus Prony series. You could switch to the numerical mode and do the same thing. It's going to take a little bit longer because you are calling Abaqus standard in this lightweight fashion. And that word lightweight, I want to make clear, we're not having to run through the solver. So that's part of what makes it very lightweight. Thinking a little bit more into the future, for instance, we could advance this tool to do the calibration of a spot weld. And in fact, we could calibrate a spot weld with real test data from a spot weld, or we could do a detailed FE analysis, as shown here in this image in the lower left. If we did a series of FE analyses of that spot weld, if we had good confidence in that, we could actually calibrate a simple connector representation of that spot weld. So now we what's coming into play is the idea of different representations, that is, different abstractions of the behavior. And we could build the abstracted behavior, the connector behavior, from either test data, or if you didn't have that test data, detailed FEA results. Another area that we're already thinking about and fleshing out is the idea of calibrating multi-scale material models. We've already worked on mean field homogenization in Abaqus standard, and we have in Abaqus CAE what is called an FE-RVE tool. And more as you dive into materials like traditional aerospace composites, like traditional injection molded fiber reinforced plastics, there's often a microstructure or structure, and we can take information about that structure and build much more advanced material models. And we're certainly planning on extending our calibration app to those kinds of domains. So with that, I'm going to stop there and then go into the demo phase of this presentation. Right here, you can see my screen is the 3DEXPERIENCE platform. And if I went to the V+R quadrant, that is the south quadrant of this little compass in the upper left hand, if I were to click on V+R, this is the icon that represents the Material Calibration app. And it's meant to be a little test machine that you'd see in a test lab, and the output of that test machine with some sort of stress strain curve. And in general, I would click on this icon to start my calibration journey or process. And for now, I'm just going to put that away. And to save time, we have put a lot of energy into thinking about how to import test data. The import of the test data, I'm not going to demo that today because the videos on the learning community do a very nice job of that, and I'm just going to save a little time. But you would use this icon right here to import test data, and we can import test data from Excel files, from CSV files, and from ASCII text files. And we've put, again, a lot of thought into that, and we think we've come up with a scheme that is very convenient to use, very easy to use, and yet relatively full-featured and powerful. Sometimes you don't have test data for certain kinds of responses, but you'd still like to see how your math model responds. And so this next icon is what we call range response data. It's not test data, but it's sort of like test data in the sense that it's strain or time strain data for which you'd like to see a response of the math model. So it can't be used for calibration, but it can be used to better understand how your material behaves outside of the scope of your test data. One of the most common uses for this would be, for instance, simple hyperelasticity. I bring in some monotonic uniaxial strain data. I fit a material model, but I say to myself, well, I don't have equal biaxial test data, but I'd like to see how my math model responds in the equal biaxial mode. I could drop down into this tool and define that equal biaxial range response data and plot the response of the math model. The next icon is how you actually select your material model, and when you go to select that material model, the list that you get will depend on whether your execution mode is in the analytical mode or the numerical mode. And so with this symbol right here, f of x, that's meant to imply you're in the analytical mode. This icon right here is the one you would use to execute the calibration. So now let's just walk through a quick demo. I've already imported the test data to save some time. This is a family of test data for butyl rubber. The plot of all the data in the legend, it shows the strain rate in reciprocal seconds. So I have a strain rate of this curve here is 0.01, then 0.1, then 1, then 10, and the fastest rate curve, the stiffest, is at a strain rate of 40. I've generated another plot. You can generate as many plots as you want using this icon right here. So I've created a second plot because I like to often see rate data as stress versus time. And I also like to see it in log. So we can go in here to the settings, and we can change, for instance, whether we want to view in a log scale. In a non-log scale, so much of it rides right along the y-axis that it's handy to have a log scale plot. And this is used very commonly when you're dealing with Prony series. You'd like to see what the span of time is in your test data. What you'd really like to know is the span of viscous behavior of the material, but often as a surrogate for that, the time span of your test data serves as the surrogate. So let's choose our material model. These are all the material models available in the analytic kernel or analytical mode, and we're going to simply choose hyperelastic viscoelastic. Let me stop for a moment and say that is our target. But one thing when you're working on calibration, it's often very handy to work in some sort of sequential order. So I'm going to just briefly here, I'm going to select a whole variety of test data and not plot it. So I'm going to only plot the fast test data. I'm going to not use, by unclicking them, saying I'm not going to use those. And the very first thing I might do is simply say, let's choose a hyperelastic model. And let's fit it to the fast data. In fact, I'm going to fit it just to the early portion of the fast data. And I often will use a Yo model. And one thing, a calibration tool, we do want the backbone of optimization to perform the calibration, but we also want the user to be able to supply as much guidance towards getting to a close enough answer. The more the user knows about the underlying equations, the better. And I happen to know from years of experience, first of all, I might take a couple stabs. So this black line, and I can change that to say a black solid line. I'd like to get this black line, which is the math model response, right as close to this red line as possible. Actually, I'm just going to fit it to here because I think there is still viscous behavior in the rest of the curve. And so, for instance, I could type in 1, hit return. I could type in 2, hit return. And again, remember, I'm aiming to capture this. In the end, I've settled on the idea that I think 4 is a reasonably good value. I could maybe go higher, but for right now, I'll leave it at 4. And I have some rules of thumb for a Yo model that often work, which is that the second coefficient is a small negative number, oftentimes around 10% of the first coefficient. And the third coefficient, the C30 value, is often again, a small number, but a small positive number. So using some rules of thumb that one has from historical background, I could say that this is a pretty reasonable fit just to this low area. And then what I can do is I can turn back on all this test data and go back and show all this test data, which I do by making a few choices here in this dialog. Again, because this math model is not time dependent yet, all of the responses lie right on top of each other. So let's go into our material selection, and rather than selecting hyperelasticity, let's select hyperviscoelastic or hyperprony, meaning linear viscoelasticity, and let's say OK. And there are some heuristics in our tool. We do try to always provide some initial values of the parameters, and we try to, where we can, make some of those choices using some intelligence or some heuristics. And so we look at the underlying test data, and I'm just turning on some responses here. We look at the underlying test data and we make a guess at what we think are the right taus of our Prony series and what a reasonable guess at an initial set of G's might be. This is a pretty reasonable guess, but having some experience with this test data, I'm actually going to ask for 5 Prony series. It's very common that the taus are not a very sensitive parameter. Whether the tau is 10 or 11 doesn't really matter. It matters whether the tau is, say, 10 or 100. And so it's a kind of a good best practice to leave the taus alone, at least initially, in the calibration process. This icon is used to show or not show all of the design variables. So the taus, if they were checked like this, that's a design variable. By being unchecked, it's saying hold that constant, don't use it as a design variable during calibration. So I can click that and I get a much more compact view. And in fact, I'm going to, for the first pass here, I'm going to select these to be off. So the only thing I'm calibrating is the 5G values. And at this point, I'm simply going to say calibrate. And I get a really nice, quite a reasonable answer. And I could fine tune this by going back and turning the hyperelasticity, the 3 hyperelastic values back on and do another calibration. But this calibration is quite nice. We show the overall error norm. Again, I haven't done a lot of telling you much about the optimization process. We want this tool to be useful for casual users as well as advanced expert users. And so there is a lot of depth we could go to in talking about the error norms, talking about the optimization procedures that are available to you. But at first, I just wanted to focus on, we bring in some test data, we select a material model, and we perhaps vary some of the parameters by hand if we have some experience with that material model, and then we run a calibration. And that's what I've demoed for you right here. We do, for each of the pieces of test data, we have an error norm, and that error norm defaults here to the unweighted coefficient of determination. And we could change that if we have a preference for a different kind of error norm. And we also have a default value for the optimization procedure itself, and you could change that if you have some deeper knowledge of optimization methods. So with that, I'm going to switch gears a little bit, and I guess I'll say this icon, optimization controls, is how I would get at all these advanced features. And I don't want to spend a lot of time here, but I do want to let you know we've given a lot of thought to this, based on a lot of years of feedback around our Abaqus CAE tools. We have a number of error norms available to you, and we have a variety of optimization procedures or optimization solvers, if you will. And I did in the slides talk about material stability. Material stability can be shown by clicking on this icon down here in the lower bar. And by default, this button is not clicked, which means the process does not try to enforce stability. But if I were to check this, I could start enforcing both I try to find the best parameters, not only to match the test data, but to satisfy Drucker stability. And I guess getting into some of that is a lesson for a later time. So let me switch gears a little bit. This is an elastoplastic material. This is actually a 1018 steel. There's a couple of bad things about this test data. There was something funny going on during the test. Sometimes during the test, there's a little slack in the machine. There's some slack in the way the crosshead or the fixturing is set up. Every once in a while, it could be actually the grip was slipping. And we see a little bit of data, a few data points we might want to delete. And also the aspect, and I would hope maybe many of you on the call know this, that for metal plasticity, it's really not appropriate to use test information past the necking point or past ultimate. And so I'm gonna get rid of the data that's out here as I go to fit my elastoplasticity. So if I just double left clicked here, it would bring up my test data. And here is how I could start to decimate or zero shift or smooth or otherwise change my test data. So I'm going to do a zero shift, and you'll notice, and I'm going to zoom in just a little bit into my data. And so whatever was going on here in the test machine, this was something bad. This was not reflecting the stiffness, the early stiffness of the material. The early stiffness is really much more indicated by all of these points. And so I'm going to come in and say that I think these points right here, the whole zero shift is based on the user selecting a trusted area of data. So I think these 4 points that I've selected, I can trust that they are well representative. And what we're going to do is we're going to back extrapolate that to the x-axis and then shift all the data. So we'll say evaluate, and that back extrapolation and shift was happening and shown to you in green. I can reset the zoom, and I can say, yes, I like that. So let's accept that. I can continue doing other operations before I say either cancel or OK. One thing I'm going to do is I'm going to say remove that. That looked like an odd point. And then I'm going to go in and I'm going to select all these points and again say remove. And then I'm going to say OK. And now I have a set of data that I think is really representative, getting rid of some test issues. And I'm going to go, and notice now I'm in the numerical mode. I've changed to numerical mode, and it gives me these little bars as a symbol of the fact that I'm integrating numerically. And I'm going to, now my material choices are all of these choices, and I'm going to choose elastoplasticity. And that material, that elastoplasticity, is not a final selection because I in fact have support for all of these kinds of elastoplasticity. And I'm going to go ahead and leave the choice being the isotropic Johnson-Cook. Again, we have some heuristics where we fit through the first couple of points the elastic modulus. But another thing that might happen here is you might have your own value of the modulus, and you could certainly just type that in, say from a handbook value that you've agreed within your company to use. And oftentimes I would not do the calibration of the modulus because in fact I might, for instance, let's just say 200 gigapascals. So let's, with just the A, B, and N values of a Johnson-Cook model, we could press calibrate right now, or again, if we know something about this, A is really the virgin yield. So if I made A smaller, it means this point would come down. If I made A larger, it would go up. B has a little bit of an effect on the slope, and I just happen to know that from my past use of the Johnson-Cook set of equations. And I could, for instance, change that to 300. And notice how the slope in this region kind of raised up. I could change it to 500. And now I'll just go ahead and calibrate. And this will take on the order of about 20 seconds. So let's just bear with me for the next 20 seconds. And our calibration history will start showing up in this box. Because we're in the numerical mode, we are running Abaqus standard. Again, we're running it in a very lightweight fashion. And we're starting to see the objective value or the error norm change. And now we're done. And this took about 26 seconds. The overall error norm is very good. The perfect fit using an R squared is 1. So we're getting very close to 1. Our fit is quite nice. One last thing to tell you a few other things. If you were happy with this calibration and you wanted to simply export this material model, that is all these coefficients, export it to for use within the platform, you would use this tool right here. If you wanted to export it to a snippet of an Abaqus input file for use outside of the platform, you could just click here, and it expects you to give I would give a file name, and I might name it, steel.imp, and I could say OK, and it would go off and create that file, and it would just be a very small file of the material cards, if you will. One last thing I could do is I could go back. We do have this capability to edit, to revert back to the original test data, and we only have one level of revert. It gets you back to the absolute original test data. And by saying OK, which I've done here, I could go back and see the original test data, all of it, recognize that this Johnson-Cook model was created from that subset of the data, which is the right thing to do, which is the best practice right thing to do. One last calibration, and this is getting to be a fairly complex one, and so I don't have the time to really go through this in detail, but this is covered on the learning community. This is a variety of test data on a polypropylene material, so that's a thermoplastic material, and the data is one fast pull test, and I'll just come in and change the color, and I'll change the color of the fast pull test to black. So I like to show test data as just dots and then math model responses as solid lines. So I have one fast monotonic pull test at 100 reciprocal seconds, and I have 3 stress relaxation tests. So again, I've plotted it along I could plot this not using a log scale. So there's your sort of classic look of a stress relaxation test. But in order to see how much time is spanned by this, it's a little easier to view it in log scale. And those are the stress relaxation test data. That's actually these 3 pieces of data. So if you're not used to looking at stress relaxation data in a stress strain plot, it's a little unusual. This is where we stopped and the stress starts decaying as the strain was held constant. So we're in the numerical mode again, and we would go in, and again, we might follow a very common process. We might first just fit a hyperelastic model to the high rate data. And then having we could go ahead and do that. We could say, in fact, I'll show you something. At first, we won't even calibrate anything. We'll just say, okay, hyperelastic material model and all of its parameters will show up here. I'm going to use a really simple 1 coefficient, that is 1 deviatoric coefficient. And this set of initial values is really done for elastomers, and this is not an elastomer, so this value is way too small. And I might say, well, let's go up to 5. This is the math response down here. 5 is still way too small. Let's go up to 500. Okay, so 500 is getting better. Let's go to maybe 600. And I can, in fact, avoid doing any this is what I might call a by hand calibration. And at some point, I might even say, well, let's go to 700. And again, what I'm trying to do is fit this black response line just to this area, because I think there might still be a little bit of viscous behavior out here at the end of that test at longer times. And then I could go in and I could say, let's choose the parallel rheological framework model. We're not going to add plasticity or anything else. We're just going to have the PRF model. But one thing the tool will do is it will remember this part. So as we say, okay, it will promote this material model to a PRF model, but it'll remember the work that we did, and it will automatically make some heuristic estimates of what these parameters might do. And in this case, we actually fill in a minimum and maximum values for you as well. So this is my initial starting point. I do have, I need to turn the responses here. So this is I've done a little bit of calibration to get my C10 value good. I haven't done any calibration here. These are just the initial guesses that the software provides. And I could go off and say calibrate, and that will, okay. So I'm using the particle swarm. That's nice that this error came up. What it's telling me is I can't use the particle swarm optimization method unless there is a minimum and maximum on all design variables. Well, I didn't intend, I forgot to turn that off. I actually don't want the C10 to be a design variable. So now let's calibrate. And I'm not going to leave this calibration will now take on the order of between 10 and 15 minutes, because you are calling Abaqus standard and you are using quite a lot of test data as well as a fairly advanced material model. So in times, for just exactly that reason and for some other reasons, we do have this ability to stop the calibration. And I'm going to go ahead and stop the calibration. And after a little bit of, it'll tell you that the user has stopped the calibration. And what I'm going to, I did this calibration earlier this morning, and I just wanted to show you say okay to that. And I wanted to share with you, if I had let that run for 10, 12, 15 minutes, I would have got this response. So again, all the stress relaxation curves are matched up quite nicely. This just used a one-term PRF, or you could call it 2 terms because there's the equilibrium or zeroth network, and then an additional one viscous network. Okay, so depending on the semantics, this is definitely a one-term viscoelasticity or two network model. And we could promote this to being two networks, and of course the calibration would get much more difficult after, well, and then take longer after that. So, and that's just, again, this was just a saved image from having completed that calibration. I think at this point we're fairly well on schedule and on time, and that really concludes the presentation material I had scheduled for today. So I think it's a great time to open things up to questions. And I need to just change my focus a little bit to looking at the Q&A box and see if we do have some questions. And I'll go ahead and read a few of the questions. One of the first questions from Prasad was, is development inside Abaqus CA stopped and now it is on this platform? Well, what I can tell you is that for a variety of reasons, any calibration activities is going on just within the 3DEXPERIENCE platform. What I'd like to say to everyone is that I certainly am a longtime Abaqus user, a longtime employee of SIMULIA, and have a very big affinity to all of our Abaqus standard and explicit customers and users. I would say the perfect way for you as an Abaqus customer, if your company has not decided to use the 3DEXPERIENCE platform, give this a try on the cloud. You can get a trial license of the cloud. There's a little bit of software you'd have to install on your machine, and then you would have access to this tool. So I would encourage you to try it on the cloud, and that gets around the issues of having to have any real heavy installation of the 3DEXPERIENCE platform. Is it possible to use this app with user material subroutines? Yes, it is. So going back to our material choice, I would make this choice of a user material and say, okay, well, first of all, a user material feature has to have a DLL of the user subroutine attached in the 3DEXPERIENCE platform. I will put together a video of performing a simple UMAT calibration and post it on the learning community. Let's another question. Is it possible to calibrate creeping data with this tool? It is. Yes, it is. In fact, I have some very nice data of creep of a thermoplastic that I'll try to get on the learning community. There is one slight thing I think I should make clear is we do think in terms of the time and strain as knowns and the stresses as the unknowns, and that becomes a little counterintuitive because the creep experiment, you think of the stress as the known and the strain as the dependent variable. But within the scope of thinking of this time and strain as the independent thing and the stress as the dependent, we can solve and calibrate creep, and I'll try to put an example of that on the learning community. How can I obtain this material calibration app to show on my 3DEXPERIENCE platform? Talk to your salespeople about that, or either your salespeople or anyone that is in supporting you. Export of nominal stress strain curve to input file includes conversion to engineering stress strain data. Yes, it does, and it also would include. If I go to this tool, it will get written out. We also have this little units business right here, and I tend to like to work in a millimeter megapascal unit system. When I export that to input file, it will be written out in these units specifically, and there will be a header telling you what the units were when it was written out. Let me move on to another question. Can we use the calibration app with complex loadings? For example, tensile test in the axisymmetric round bars, which would require a detailed FEA simulation. Okay, well, so far the tool in its current state is assuming a homogeneous state of stress and strain in the measured region. So can you deal with complex loadings? Well, the simple answer is yes, because I could have a very complex loading. Say I could load it, hold it, load it, hold it, unload it, hold it, unload it some more, hold it, and even go into the negative, and then even put a specimen into compression. And I could bring that in and calibrate it, but the tool so far assumes a homogeneous state of stress and strain in the measured region. So can this tool be used for situations in which, for instance, necking occurs and you have a very inhomogeneous state of stress and strain? No, it cannot. That is on our roadmap, and we will be working on that in the months ahead. Is this material calibration app available outside the 3DEXPERIENCE platform? No, it is not. And again, like I said, the best way to if your company does not use the 3DEXPERIENCE platform, I would suggest that you ask for a trial of this on the cloud. What is the difference between instantaneous and long-term time scale? Yes, you saw that in anything that has a, you saw that right, you saw that in a PRF or a hyperprony model. It really talks about instantaneous versus long-term. And this is nomenclature that's common to Abaqus. It's not, we didn't dream this wordage up. So you would tell it whether your hyperelastic model comes from a very high rate test or a very low rate test. And again, if you have further questions about that, please either just contact me or contact your support office. There are a lot more questions, and I'll try to read down this fairly quickly here. Is the calibration app only available on the cloud? Oh, no, I didn't mean to say that. It is available both on-premise and on cloud. And of course, one of the challenges about on-premise, if your company is already using the 3DEXPERIENCE platform, that means you can get access to this calibration app. But the calibration app is relatively new, and your company would have to upgrade and move to fairly new versions of the 3DEXPERIENCE platform. So the calibration app is part of on-premise and on cloud, and the on cloud is maybe just the faster way of getting access. Which role gives access to this app? The role is the trigram MAS. So if you told your salespeople, can I get access to the I think it's also called the Material Calibration Specialist, but the trigram is MAS. Is it possible to fit a larger sample size of test data, or do I need to do this prior? By larger, I'm not exactly sure what the user meant, but by larger, we have imported into this tool data sets as large as 1 million data points. We've also loaded into this tool, imported into this tool, multiple data sets of 100,000 data points. And then we would decimate it in this tool. Dragging around 100,000 data points for pretty much any material model is just wasteful. And especially if you're using the numerical mode, is going to really degrade your calibration times. That's maybe a good subject to have something in the learning community about. I have personally brought in as many data sets as about 13. I had a thermoplastic in which I had both creep data and I had rate data. And in fact, I had data across temperatures. So I had as many as 13, but there's no fixed number on the maximum number of data sets. Does an academic user could also use this app? I would just simply say, please talk to your SIMULIA contact, your sales people about that. I believe the answer should be yes. Are there plans to include concrete material? we certainly are thinking a lot about where we're going next with this, and I think we've opened the door to a lot of Abaqus standard material models because we did this lightweight stress evaluator. We certainly will aim towards material models that are requested most by our customers, and we're already adding rate dependence for elastoplasticity. We're already working on damage and failure models. We already have on our list of roadmaps crushable foam. That was an often requested material model, and there's many people using crushable foams, most often perhaps in the packaging industries, and they have a hard time calibrating those. So I guess at this point, we will consider everything, and we'll consider materials kind of in an order of preference set by interactions with customers. Are the slides available to distribute to the audience? Well, first of all, this entire eSeminar is being recorded and will be made available. And I will put the slides on the learning community. I'll reorganize the posts a little bit, and I'll put these slides. These certainly are slides that are available to the public, and I'll put them on the learning community so that you could grab them from there. I believe with that, maybe one other question. Can I calibrate an Abaqus explicit material model? Well, if there's not really. If that material model is both in Abaqus explicit and in Abaqus standard, then the answer is yes, you can. But let's say you had a material model that was only available in explicit. Because in this numerical mode we're using, we're actually calling Abaqus standard. The answer for now is if that material model is only in Abaqus explicit, no, it won't be available in the calibration tool. That is something we're thinking about for the future. Can the calibration app calibrate a rate-dependent resilient foam, that is elastomeric foam? Yes, it can. You'd have to do that in this is the analytical mode. You can do hyperelastic viscoelastic, but you cannot do hyperfoam viscoelastic in the analytic mode. But if you were to change to the numerical mode, which is shown here, then under hyperfoams, you in fact could do hyperfoam viscoelastic. I believe I'm reading down through this long list, and some of the questions were similar, and I've tried to answer one or two questions by giving a single answer to them. But I believe I've answered all of the questions that were posed. So we're fairly much right on time. If you do think of other questions, you could either post them to the learning community, or you could address them to me directly, and I'd be happy to answer further questions. And with that, Vanessa, I would say that seeing no further questions, I would say we're done, and we're done pretty much right on time.
Yes, thank you, Todd, and have a nice day.
Okay, thank you everyone for attending.
Bye.
Bye.